Okay, so here we are the end of the course. So 12 weeks of learning MATLAB and numerical computations using MATLAB. Like MATLAB is like just a language, but like the main thing which we have learned is numerical methods and how to apply these numerical methods. Okay, next assignment 12 1. So we have learned about numerical methods and how to use these numerical methods to solve problems in engineering or research using MATLAB. So yesterday we were discussing about this PDs, I think. Yeah. Uh, Abhishek is asking about problem 1B. Yeah. I'll just take this and then go to revise things. Take this one. And okay. So here we have to do Newton-Raphson for this W minus UC uh, minus K roots. So instead of C, I'll take this as C itself, X itself. W, I'll substitute it here. UC is QX. So Q is 0.1 into X. And what is this? K root C, which is K into K is 0.25 into square root of X. So this is our uh, nonlinear equation, and we have to solve it. And these are the parameters which we have already substituted, and we are going to use forward difference formula. Using forward differences, instead of taking this, we'll take this, and this will become h. So x plus h, f of x plus h minus f of x by h. That's the forward difference. And We have to take 0.001, 0.001, and the initial value is C naught is 25, so that is also we have to change. And so this you can do. This is just directly substituted. Uh, Instead of C, substitute 25, you'll get the answer. And report the numerical difference. Okay. Yeah. Then he is also asking then they are asking to also report this numerical difference. So numerical derivative we have to give for the first iteration and then compute, go for the next iteration, and then we have to tell out. So it has to go below 10 to the power of like minus 4. So that's what we have to do. Like this, like uh, they are asking to report error at every step. So we have defined everything, like error is defined at every step. So if I run this, run the section, it's not, it's not this. Right. We have defined. Ah, I'll just, I want to use this. I'll just use display uh, uh, numerical differentiation. Numerical differentiation at iteration is we can use this and we can print num2 str nd. What was that? Df. Now we run this. Okay. So this is the numerical iteration at uh, uh, first step, which is this is minus 0 point. Sorry, this has to give some space. In, yeah, wait, wait, yeah, just add. We'll see. Okay, so this is the numerical differentiation value, uh, and I think FC you can calculate. Uh, I don't need to do it. And this is the error at first iteration. So these are all done. And then we have to go and compute C2. This is our C2, 34.734. And here the error is 0.26597. And C3, we have to compute. And C3 is this 34.7339. And error is again 0.33, 0.001363. And repeat for one more iteration. So if you repeat it, like you'll get this error. So only the error you have to do. So that's what this problem was. Hope it is clear. 1A and 1B. Abhishek, we fine or do you have a Abhishek? Are you here? One answer you got. Which answer? I didn't understand which answer. Like which answer you got? You got this one. One no, answer one. Yeah, yeah. You substitute it like uh, NR fun of NR fun of what was that? 25. So you are getting 0.7. You'll get 0.7. At initial point, the value of FC is 0.7. 0.75 is the answer, not 1 point minus 1.75. Because this is 2 minus 0.1 into C minus K root. So you have to just substitute the x value here. Everything else remains same. So you have to just substitute the x value and you will get the answer. So x value is 25. So if you take 25 and you substitute FC, you will get this value. 0.7. Okay. What else? This is clear, right? I hope that solves. Okay. Okay. So Now we will see a little bit about a very important thing which we couldn't cover. Uh, is and it will be very helpful for someone who is like working on fluid dynamics or like uh, finite element, all these things, or like if one like lot in lot of areas basically like so it can be very helpful in many ways. So that's what our uh, today's discussion a little bit of it. We will see this and then we will also try to revise everything which we have covered in the course, like whatever we can. So I am just trying to cover this because this is a very important thing, like how to handle tridiagonal matrices uh, would be would prove to be quite important, like in many cases, because like lot of matrices have spars. So we'll see. So tridiagonal matrix algorithm. We can also call this the Thomas algorithm. Huh. So, so basically, when we are like solving any differential equations using uh, our numerical methods, like you want to convert like let's say partial differential equation or a ordinary differential equation, and you want to solve it using numerical methods, like we can use the central difference scheme, like for lot of different techniques we have seen like in the last week or in the before week. So we have something like we have, let's say, steady state heat conduction equation, which is d square t by dx square equals to gamma into t minus 25, and we have two boundary conditions. So this we have also seen yesterday. These are the two boundary conditions. So in this case, what we do, like we we will, we generally what we do, like in order to solve this, we use the central difference formula. Like we will divide our uh, this into some segments. Like we will divide our segment into, sorry, we divide our domain into some number of segments. Like let's say this is a rod, and you are dividing it into, instead of solving for the whole rod, we will solve only for the nodes of this rod. Like so, that's what discretization we are doing it to solve it numerically. Like instead of solving for the whole rod. So if like now we can what we do is like we take, let's say these are the nodes 4, 5, 6, 7, 8, and 9. 9 nodes are there, and there are 8 segments. So this is the first segment, third, fourth segment or element, like whatever you want to call it. So these are like 8 elements, and there are like each node will have some t value which we have to find out. So t1 is already given, which is 100, and t9 is like 25. So in between the values which we have to find out, and we know that this governing equation is uh, explaining the phenomena of heat dissipation in the rod. So like as we move along the length of the rod, so we can see how temperature is varying by using this differential equation. This differential equation explains how the temperature is. So uh, if we solve this differential equation, we can get temperature. Like if you integrate it two times, you can get the value of the temperature. So of course, like this, we can solve it numerically, uh, analytically also, just by integrating. And you have two boundary conditions, two integrating constants will get, and we have two boundary conditions. We can get those in, using these boundary conditions, we can go at this integrating constants also, and we can solve it. You can get a closed form solution. But like many times, it is not possible to do this. You won't have there will be a lot of complex problems. You won't be able to do integrations. So like analytically integrating is like impossible. Not every functions can be integrable. So there might be like very complex functions which can't integrate. So it's like humanly not possible. Like if you have also like a very good like a very lengthy integration, uh, that also it's uh, basically it's killing your time, like wasting it. Like instead of that, you can delegate it to a computer. It will solve it in a better manner. But as we said, instead of taking the analytical route, like we can also do it numerically. So the advantage of doing it numerically is uh, it's like computationally efficient, and also you can do it for any function. Like whatever the right hand side is there, like you can do it, like you can numerically integrate it uh, like anyhow. But in this uh, numerical techniques, we also have some error because of the discretization which we are doing. So we won't get the exact values. Like of course, there will be a slight error. So that is a compromise which we have to make. So what we did is like we use the central difference formula. So let's say at any point on this, at any node xi, this is what we were getting, right? So this we were using the central difference formula, and this was what we were getting. So if I let's say want to solve this for mm, like now I'll take this and I'll substitute it here. Ti minus 1 by h square is equals to gamma into Ti minus 20. So I want to get the temperatures at T2, T3, T4, node 4, node 5, node 6, node 7, and node 8. So now what I'll apply this algorithm, central difference scheme at point 1 to point at point 2 to from point 2 to point from 2 to from I is equals to 2 to I is equals to 8. We will apply this. So you will get initially you will get T2 minus 2 T1 plus uh, what is this T2 minus sorry, this is 3T, uh, this is T2, sorry, T2 plus T1 divided by h square is equals to gamma into Ti we know here already. So like this is T1 we know already, which is like, and then we also go for the next point, which is uh, T4 minus 233 plus T2 by h square. So like this we go and do it till point 8, which is node 8, is 7 by h square. So you will get So we will get like some, and then we can also write take the value at uh, uh, first and the second for I is equals to 1, we know T1 is equals to 25 and T uh, for I is equals to 9, we know T9 is equals to uh, how much was it? This was 100, sorry, and this is 25. So now, like if I want to get all the values from T2 to T9, T2 to T8, I can take this, like I can take this system of equations, like I have some nine system of equations. I can convert this into a matrix, right? So like I can convert this into a matrix because uh, T2 is here and T2 is also here, like elements of each like all the equations are coupled, and like all the equations are related to each other. So that's why we have to solve like get solve this all the equations simultaneously. These are a system of linear equations and we can solve them using any uh, like linear equation solver. So after that, like we get a matrix like this. So we get like you will get uh, T1 0 something something, and like you'll get I think 1 here. So this is 1 0 0 0, and then you will get uh, T 1 minus 2 3 1 minus 2 1 0 0 0, and then you will get something like something like this. So by discretization, and then if we take all the system of linear equations and we have to solve it, we get some kind of matrix like this. So this is like I have just written for 2 rows, but the basic structure of matrix by doing this discretization looks like this. So this is what it looks like D1 U1 something like this 0 0 0, and L2 D2 U2 and 0 0 0, and here 0 0, and here X 0 0, and like here diagonal entries will be there, and apart from that, like near diagonal entries will be there, and apart from that, away from the diagonal, everything is like 0. So and this is, let's say, A, and this is B. This is the right hand side vector which uh, we know. So this kind of matrix will get. So the thing is, this is a very sparse matrix. So this you can also call it as a banded matrix. So in finite element or also in computational fluid dynamics, like in also in finite volume method, you will get, it's common to get these kind of matrices where near the diagonal you have populated matrix, but away from the diagonal, like everything else is 0. So the thing is like uh, because of these zeros, like if you, let's say, like I'm just taking 29 8 segments here. If I take, let's say, 100 segments, like this matrix will become huge, and 100 cross 100 101 cross 101 is like it will be like the size of matrix will blow up. But uh, in addition to this, like the zeros will also get increased. So as the size of it increases, like you have to store a lot of zeros. Like this is like waste of memory uh, in the computer. Like there is like, if you have these many zeros, like why to like store them if they are like not very useful. So what can we do is like here in this case, we have three diagonals. Like one is the main diagonal we have. This is our main diagonal, D, and then we have our U, which is like values of U, uh, which is our, and then we have L, which is our, this is our subdiagonal, and then we have the diagonal, and then we have the super diagonal. U is our super diagonal, and L is a subdiagonal, and D is the diagonal, main diagonal. So now I can take only the U values and I can store it as a one-dimensional array. One-dimensional array, or like a single, like you can save all the values of U as a single column matrix or a vector matrix, like this you can save. Basically, we'll save it as a column matrix. So L also, I can take all the values of L in this matrix and I can save it as a column matrix. And D also, I'll do the same thing. So this is like this way of saving this matrix, like the coefficient of the matrix, coefficient of the equations is saving, will save us lot of memory in the computer. Like I am not saving zeros, which are like not useful to me at all. So that's what is one advantage of saving like this. And then like when solve using Gauss elimination, so like you know, right, like we take a matrix in Gauss elimination, we take first row and we normalize it, like we divide the first element by we divide the first row by the first element of the matrix, and then we take, go to the second row and we try to take let's say this is A11, A12, and A2, A13, and this is A. I'll just take a second order matrix. A is equals to A11, A12, A21, and A22. Okay. So now if I have to solve using the Gauss elimination, so what we do first, we take, divide the first row by let's say we also have B. So we take the augmented matrix A, B, which looks like this: A12, A21, A22. So, and this is our B1 and B2. So if I want to solve this system of linear equations using the Gauss elimination method, so what we do, we first take the row 1, and we divide it by A11. So that is the first step we do. And then you will get something like this: 1 divided by A12 divided by A11. Let's say I'll just call this as A12 first, and this is B1, 1. And it's write it like this. And then the second step we do is we take row 2 and we apply the transformation, row transformation, which is R2 minus A21 into R1. So each element of row 2 is subtracted by multiplying R1 with A21. So now you will get something like this will become 0, and this you will get, let's say, something like A221, some kind of thing you will get, and then you will get B1 minus B22. So after doing the transformation. And then we do the back substitution, which is we get A22 is equals to uh, uh, let's say we have to solve for x and y. Then we get y is equals to B22 by A221, and then we substitute this y, and we get like we can also get x. So do the back substitution and get the x, y, and values. So, but this is a very small matrix. So, like basically, I have to do like lot of multiplications and subtractions. Like first I am doing here. First I am doing here. How many divisions? One, two, three. Three divisions I am doing. So in these steps, I am doing three divisions, and then I am doing uh, three multiplications and three subtractions in the second step. Three multiplications and three subtractions. So total, I have to do how many? Uh, nine nine computations here. So our matrix size is n is equals to 3, and this you are getting of order 3 square. So order of computational complexity is n square. Let's say if you have, let's say, some matrix like this big matrix only we have. So banded matrix we have, and there are like lot of zeros. Let's say you have a matrix of 1000 cross 1000. Now your computational complexity will be n square, which is you have to do how many? 10 to the power of 6 computations you have to do. So you can see how with the increase of size, the computational complexity increases by square of the size of the matrix. So, but the thing with this, like, the thing with this is, I don't need I don't need that much computations to compute to solve this tridiagonal matrix, because there are a lot of zeros which we don't need to do anything. Like we don't need to do calculation with these zeros. So, like if I just do computations for these diagonals, it will be enough for me. So that's what tridiagonal matrix Thomas algorithm does. So in this, let's say we have something like this. Our A is I'll take the augmented matrix, and this is our diagonal. This is our U1. This is L2. This is D2, and this is U2. Let's say you have something like this. Uh, something you will get, and you have L3, D3, U3, 0, 0, 0. 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. Let's say 7. We'll go till D7, and we'll get how much? U6 will get. These things will be there. Other things are 0, and get is up to uh, L7, D7. And we also have our B, which is B1. let's say up to bn. So now you, if I apply the Gauss elimination thing, like now you see, like I don't need to divide zero with, I don't need to divide zero with like first transformation if I'm doing in the Gauss elimination. I don't need to divide these zero elements in the first row with D1 because these are already zero. Like it's no point of doing it. So it's just a waste of time to uh, do these calculations like dividing by zero. Similarly, in the second, like after doing the first row transformation, like you just need how many? Two divisions here. Like if I just do two divisions, it's enough for me. I just do two divisions, it's enough for me. So instead of doing eight divisions, I'm just doing two divisions. So then after that, I have to do the transformations in the second row. So where you can see like I have to just subtract in this. Uh, if I just subtract these two, like if I just multiply and subtract these two, it will be enough. Like if I do two multiplications, because multiplying this zero with like again something will be zero, so it's no need to multiply this with zero with something. So I'll just multiply d1 with uh, d1 with L2 and u1 with L2 and do the subtractions. So it's just enough to do how many? Two divisions and uh, uh, two subtraction. So it's like uh, you are getting how much? Uh, 2 plus 4. So the max, like we have reduced the number of computations to 6 here. So otherwise, we could have how many computations we could have done? We could have done 8 divisions here plus 8 divisions plus 8 subtractions. We could have done how much? Uh, 24, 24 uh, divisions you could have done. So here also we have one more division here also. So that I forgot. So we need to here include this also. So three divisions and D also we need to include, and this uh, here we'll get yeah three multiplications and three subtractions. Yeah, three multiplications is six. So get nine, something like this. So the order of computations like it decreases drastically. We are like decreasing the order of computation. So this is like 27 and this is like 9, like three times more. Like so, why to do these many computations? Like this is just wasting the computational resource, right? So if I just play with these diagonal elements and do the transformations with for only these diagonal elements, if I just apply the Gauss elimination procedure for only these diagonal elements, I can save a lot of computations and lot of time. Firstly, we are also not saving this whole matrix. We are only saving this U1, this diagonals only, upper diagonal, lower diagonal, and main diagonal. So that saves the memory. And then avoiding these computations on the zero elements in the matrix, we are also saving the computational cost of the compute of the algorithm. So that's why this will be like instead of going n square, like taking n square computations, it will take some order of n only. Like this is like 8 plus 1, like you can say order of n only. So that's what that's what it is like doing. Like we are reducing the order of computations from uh, we will write the code such that we will store only these diagonals and we will also apply the computations only to this, like we are not doing any computations for the zero elements. So that's how we will reduce the space required to save the matrix, and also we are reducing the number of computations. So this is a like very good thing, like not giving computational load, and also uh, memory space to the computer. So that's what Thomas algorithm does, and it's very important uh, for us because, like, if we are solving, like, especially in fluid dynamics problems, or or in solid finite element problems also, we get these kind of banded matrices. Or also you can say sparse matrix also you can say. Like matrices filled with lot of zeros are called sparse matrices. So this can be handled in this way. One way of this handling them is this, like you can use the tridiagonal matrix algorithm. I think there are a lot of other algorithms also to solve like various sparse matrices and also tridiagonal matrices. Like this is one algorithm, Thomas algorithm is one algorithm. So which we can use, and we can increase the computational efficiency. So we'll just see the code. This is for so this is our code. Okay, so uh, this we are like doing it for our um problem of heat conduction in the rod. So we like we'll get a matrix. So first we will, let's say, uh, I have also written this converting this. Like we have saved all the L, D, and uh, U vectors. Like what are all the diagonal uh, entries are there? We are all saving in the L, U, and D vector. So first we initially will save them, and we can also like try to print and see like what they are giving. So A is equals to tridiagonal. This is our function. If you give LDU, so it will give the full blown matrix which we solve for. So let's see. I'll just run this section. Like I'll also include CLC clear and close all. And I'll run this run section. Variable again. I don't. So this is our okay. This not this. I'll just run up to here. So this is our full blown matrix which we get. So yeah, no. So 1 and 2 plus alpha and theta. Okay. Okay. So this is our full blown matrix. We can see that there are a lot of zeros in this matrix. So this is just like if I am taking 10 elements. Let's say if I take 100 elements. So if I take 100 elements and if I just do this, So you will get some very big, like it's storing, like you can see how many zeros are there in this, like uh, it's like a very huge vector, like with so many zeros, like unnecessary, like we are saving these zeros, like it's just wasting the computer's memory. So instead of that, like you can see the size of A is 101 cross 101. Like you can, like how many elements are there? Like about 10,000 elements we are storing. But that's not necessary. Like I can just store LDU and LDU three matrices, three vectors. If I just store, like you can see, I am storing how many elements? Instead of 10,000 elements, I am storing 303 elements. So how much memory I'm saying, like just by reducing, like it's drastic change in the memory required to save the matrix here. So that's the main, like that's one of the main advantages of our tridiagonal matrix algorithm. And this is just like I'm taking like 100 elements. There are like problems in FEM, or so, like if you are like solving the computational fluid dynamics problems, you will get some millions of degrees of freedom. Like this n may go up to like some millions. So it's like that will make a lot of, like sometimes your RAM will not be able to handle and save that much matrices. Like you cannot save them. Like so, I was also doing a project in my masters. Like I was getting this kind of huge matrix with like lot of zeros, and like my memory, like the memory of my computer, like memory when I'm saying is like working memory, which is RAM, was not able to handle it, like because that was such a huge matrix, like it won't be able to handle it. But there were a lot of zeros in the matrix, so like it was wise to ignore those zeros. So like one way of doing ignoring those zeros is like just saving these diagonal elements, super diagonal, sub diagonal, and the main diagonal, and saving the memory of the computer. So that's a very good thing which we can do it to our computations. Then we can also, like then we are doing the same Gauss elimination procedure for just only the our diagonal elements. You can see the like uh, first we will divide our upper diagonal by di, and like because like the already this let's say I'm just taking it up to 10, and where was this? I'll just take 10 elements because this will be easy to show the matrix. So I'll just take 10 elements, and you can see like this is already one, so I don't need to divide by one. So I don't need to divide uh, like d1 by d1 is already one, so I don't need to divide d1 by again first row, uh, first row by d1 again, because this is already one. So that's what that one thing is already done. Like then we divide uh, u1 by d1. So first row we are dividing by the first element of the first row, all the elements. So here like one thing is like u2 is already u1 is already zero here, but okay, fine. So there will be problems you where you will get u2 also. So then we have to take care of that also. Then so that's why like then we go and divide b also, like which is our right hand side vector with di, and then we do our uh, uh, pivoting for elimination. So we take alpha because alpha I have already taken here. Like instead of alpha, I can take something like zeta. I'll call it zeta instead of alpha because like alpha we have already given some variable which was alpha. So this is just taking the first element of the second row, first element of the second row, and we are like uh, doing because this is already zero here, like for everything, like for every uh, uh, computation like this, we have to make it zero. So, like after doing the calculations, like in the row transformations, you will get Li plus 1 as zero. So, we have to make it to zero. So, and then we do this transformation for the upper diagonal and also the right hand side vector. So, that we do for we start from the first, we'll take first two rows, apply the transformation, and we'll take the second and third row, we apply the transformation, third, fourth, like we go on doing this, and we will get a uh, uh, upper triangular matrix. So, and that we can solve it using the back substitution. So, same thing what we have done in the Gauss elimination, we do it, and we can get our solutions for x and y. So, here what was x? So, x is 185.8589, 100, like all these are the values of x. Let's say if I just, instead of doing the tridiagonal matrix computation, let's say if I just do it using the inverse formula, like A by B, instead of using the tridiagonal matrix algorithm, I'll get how much, so I'll get similar kind of result. So A cross B, yeah, there is some error. Yeah, yeah, okay. So we have to save A here after we cut this and out. So X is this. Let's say if I want to uh, do it now, uh, like by taking the uh, direct uh, inverse of matrix A and B, like I'll get this is MATLAB's algorithm. So I'll get like almost same values. Like there might be a slight error, uh, like like almost there is no error. So like I am doing it. Let's say if I am taking, let's say, some 1,000 elements, or let's say I'll take 10,000 elements, and let's first solve by our uh, tridiagonal matrix algorithm. So it has been solved, and x will get something. Okay. So this is the value of x which we are getting. So it's like some big vector which we are getting. So clear this, and then I'll solve it by doing the inverse. So let's let's say A cross B. So this is also solving in the fast way, but you can see how much memory it is taking. But this won't be like this much fast, because this is a very simple matrix. And like if there are like millions of matrices, let's say I'll do one change. I'll take A here, and I'll save A here before doing the transformation. And let's say I'll take this B as our B, or let's run this, or let's say A cross B, A, like So same thing we are doing with A inverse B, and like we are also doing with uh, tridiagonal matrix algorithm. We are basically saving, like, instead of you how many, like 10,000 square elements, which is like 10 to the power of 8 elements. We are just storing the how much 30,000 elements we are storing. So lot of memory space has been decreased, and we are also decreasing the number of computations. This is like okay, like this is a simple problem. That's why like MATLAB is like able to solve it like instantly. But like if you will have millions of degrees of freedom, like then it becomes very impossible to use a slash b formula and get the uh, this method of using a slash b and getting the result to our problem is like not possible. So that's like the one intelligent way researchers have come up to basically handle this tridiagonal matrices, which are in banded form, uh, just by saving the uh, space and also by saving the computations. I I hope that was fine. That uh, will help you a lot. Like you might be getting a lot of these things, uh, especially you are like doing computational fluid dynamics problems and all these things. Then you will get this kind of banded matrices, and will save lot of things, computational resources because of this. So that was TDMA. Like I couldn't discuss it when we were doing the linear equations, because like we didn't discuss the partial differential equations. Solving differential equations was not done. So I postponed it, and like today I got time to discuss it, so I'm discussing it. Like uh, I hope that was clear. And now we also, uh, Nasir, you have any doubts before we move on? Uh, am I audible? Hello. Okay. Okay. So now we will just take a roundup of things which we have learned in this course. Uh, we have done like uh, many things. Uh, we'll just see what we have learned. Okay. So we'll do a wrap up of everything which we have learned from the first module to the last module. So firstly, we saw how to set up MATLAB. So MATLAB is a proprietary software. We have to buy the license, you get it, and then we have to download it. Like if you have the license, you can download MATLAB from mathworks.com. So that is MATLAB is uh, uh, developed by this company, MathWorks, and they like yearly, I think two times they release uh, two uh, versions of MATLAB. Like they try to develop uh, the deficiencies and improve the performance of the software, and they'll try to develop uh, and release new versions. I think like you will get 2025A version, 2025B version, like that they release. So like we can use MATLAB for a lot of things. Like you can, there are also other tools in MATLAB like Simulink, all those things. If you are, I think someone from electrical, you can also like relate with like using Simulink. Basically, we use MATLAB to write codes to solve some research problems or engineering problems. So MATLAB has its own language. Like this is a high level programming language. Uh, like more less lines of code than C, C++, and Fortran, like the other programming languages. But of course, like this is not this might not be as fast as the C++ and the Fortran, but the lines of codes are reduced, and MATLAB uh, offers a great user interface. So we have seen like it has a lot of toolboxes like functions uh, which you can use, and you can also see variables when you are solving. So all these things it offers, and because of you pay a good amount of um, license fee, you get a lot of things which you won't get in some kind of open source languages. But nowadays, the open source community is also very proactive, and like they are trying to compete with this. So you can choose anything. Like science has like very little barriers these days. Like everything is like available on the internet. You can use them. So if you are someone like who is struggling with getting the license of MATLAB, like of course we have learned MATLAB here, uh, but the main thing which we have learned is the numerical computations. So numerical computations, uh, like lot of techniques we have learned, and MATLAB was just a tool to do it. So either you go to Python, or either you go to C++, or either you go to Fortran. For doing these numerical computations, you have to write some code. Just the syntax will be different, but you will follow the same algorithm. So, like learning how to uh, understand the algorithm and write it in a step-by-step way. Like if you are someone like let's say familiar like with flowcharts, like you can write your problem and break down into like different steps. Like first you do the step one, then you go to step two, and if you are like very good at these things, then you go at the end. If you are like you are getting the result, like after following n number of steps, you will get the result at the end of any problem. So this is what humans do. Like we just break down our problem into many steps, solve each step by step, and then we finally get some result. So that's what we are also doing while we are doing the code. We are telling the computer to do this step first, to do this step second, and to do this step uh, in the end. So this is what is algorithm. So algorithm is step-by-step way of solving the problem. So this is the algorithm. So if you are able to write the algorithm for any problem, then you can solve it in any programming language. You can just learn the syntaxes of the programming language and you can solve it. So it's not a big thing, but knowing the algorithm is the most important thing. Algorithm is step-by-step way of solving the problem. Whatever the problem which you have, it might be finite element, it might be computational fluid dynamics problem, or any problem. So that's what like is the important thing which I want to tell you is like try to break down your problem into number of steps, and if you are clear with the if you are clear with the steps which the problem has to be solved, then you will be able to solve the problem regardless of anything. So you just have to write the code. That is not a big deal. Just if you are clear, you should be clear about your problem and you should be clear about how to solve the problem. Then you just give the instructions to the computer. Code is just instructions, giving the instructions to the computer. So that is like a very good learning which we can take from this course. We have learned a lot of algorithms. So numerical differentiation, ordinary differential equations, or numerical integration, linear regression, like different things. So in MATLAB, we have seen like we can write code, like we can use like uh, we can write a script file. So instead of executing your code in the command window, we can just write a script file. This script file we can use for n number of times, and we can save it and we can use a number of times. Like if you're doing writing the code in command window, it will be very difficult to edit your code and modify it and run it again. So then we also have function files. So function files, we have written a lot of functions. Like if you want to execute some block of code again and again, like in the same code or like in different codes, you can just write a function file and call that function repeated number of times. Like you can just call it. Each function will have some syntax like this. We know this is the syntax. It's an output, and you have this function, the name of the function, and then you have some inputs of the function. So this is how like we write the syntax, and you write lines of code which you want to execute again and again, and then you will give it. So that's what function help us, like function files and functions help us to do these things. And then we have also like seen variables, how to create arrays in the MATLAB, lists, all these things we have seen. So we don't need to like I don't think we need to go see, like we know the indexing in MATLAB starts from 1. So if you have a list of elements, A is equals to 1, 2, 3, something like this, then you can just an array, like you can call, if you want to just call the first element, you can just write A of 1 and you will get, sorry, this should be like this. A of 1, you will get the first element, and A of 2, you will get the second element. So like this, you can access the indices, like also matrices also can be accessed. Like let's say if you have a matrix like this, 2, 3, 4, 5, and you want to access the second row, second element of the matrix, then you can use just this. So second row, second column element of with this element I want to access, I can just use this uh, indexing and use this kind of format function code. Like if I do this, I'll execute. If I execute it, I'll get the result as 5. So like this is how we can also like uh, you can also like, let's say if you have some very big matrix, then you can also access submatrices also. So You just need to give from which index to which index or the rows, which index to which index are the columns which you want to access, and you can do it. So let's say if you want to access from second row to fifth row, and the second row to fifth row submatrix like this, then if you write the code, it like 2 is to 5, basically it goes from 2 to 5 in steps of 1. So 2, 3, 4, and 5 will be uh, covered in this indexing. So I just want to access the submatrix like this. Then it will give the submatrix which you want to access. So that's how we can do this. So we can use like matrix. MATLAB basically is like matrix laboratory. Like every computations which we do, like we use arrays or matrices to store our data and access it and do computations. So then we went to in the next, I think the third module, we went to the errors. So we saw like one error is the truncation error. So truncation error is like when I have, let's say, uh, a Taylor series, which is, let's say, at x is equals to 0, then it's called a Maclaurin series. So x into f dash of x of 0 plus x square by 2 factorial into f dash of uh, x. So f dash of sorry, f double dash 0. So like that you can write like lot of terms, like let's say sin x or cos x. You can write any function in the form of a polynomial by using the Taylor series. So like while using the Taylor series, like if I'm just taking, let's say, two or three elements, like let's say I'm just taking three elements in that Taylor series, and I'm not including this. So let's say like I can go on up to infinite I can go on up to infinite numbers in the Taylor series, but I won't take it like this will be good enough. Like this will give me a very approximate value, but there will be some error. That error is the truncation error. So you are just truncating the series, Taylor series, to get some approximation value of f of x. So this is called as truncation error. And there is also another kind of error which we can experience is the round off error. So round off error is like MATLAB has a least count or a precision. Like it cannot go beyond a certain value. Like I don't like I think 1 e power minus 16. Like like if you are dividing something like let's say, for example, if you are dividing a by b, MATLAB can go up to only this value. Like uh, it won't uh, uh, it won't give you an answer like 1e minus 32. It will go only till minus 16. So this is the last result it we can give. So if your true result is like something this, but you will if you are getting only up to here, then this is called rounding off. Like you can also relate it to like this, like you are taking, you will have lot of elements, but you can store up to only this, and you are like not storing this is rounding off. So we know this, like you might have learned about significant figures and all this, but this is just a limitation of computer, like, or the least count of your computer, you can say. So this is the rounding of error which will happen, and this truncation errors and round of errors will accumulate as we do the calculations, and they will lead to more kind of drastic uh, result changes that we should be careful of. So let's look at uh, how error propagation is done. Uh, let's say I have uh, so this is my, I'll just share the screen and I'll share the code. I'll close this, all these things. So just we'll just see how uh, this precision round of error can be uh, precision of MATLAB can be seen. Like you, if you have like, let's say A, and you are like just adding this 1 e power minus 16 to A, and if like we will just check if this A will be equal to B. So MATLAB will give a result that yes, it is equal to, right? So if this is displaying 1, because it is agreeing that A is equals to B. But we know that there is like a difference between A and B, which is 1 E. If you subtract B from A, you will get 1 E minus 16. But it won't do it because it is just doing rounding off and taking just B as 1. So that's what rounding off error is doing here. Let's say if you are like just taking instead of E power E instead of taking E minus 15, instead of E minus 16, if I will take E minus 15, let's say what will do, what will be the thing. So now it is showing that A is not equals to B. Now because B is some, MATLAB is taking the value of B because like this is above the least count of MATLAB. So there is no like rounding of error now. So A and B, it is considering as not equal and it is giving me a value of 0. So the least count of MATLAB is like generally if you have a 64-bit processor, I think you will get 1E minus 60. So if it goes anything like if you get values to this or like below this, MATLAB will just ignore it and it won't add to B and it will uh, just round off the thing. Like so that's what like rounding off is doing to us. So this and we can also have like what different kinds of errors like relative error, uh, absolute error, and the percentage error. Like let's say I'm just taking this. So let's say I am taking the value of e power 1. So that is the exact value of e. And next, I am doing an approximate, I'm taking an approximate value of e. So which is by some Taylor series expansion or uh, yeah, 1 plus 1 by 1000, uh, 1 by 10, how that is how many? 1, 2, 3, 4, 5. So 1 by 1 plus 1 by 10 power of 5 power 10 to the power of 5. So this is some exact value and this is let's say some approximate value of e. Then if you want to get the absolute error, you just take the you just take exact minus approximate and you just apply modulus of it. You get some positive value, which is the abstract, which is the absolute error. And then you also have we can also get the relative error. Relative error is we take the absolute error and we divide by the exact value of the thing which we are calculating. So that will tell how much percentage, not percentage, like how much relative your error is to the exact value. So that's what relative error, like this is how we can calculate the relative error. Then we can also get the percentage of this relative error, which is how much error we are getting in terms of the exact value. That is the percentage error. So these are like three different kinds of errors. So I can just run this. You can see like this is my absolute error and this is my relative error. and this is my percentage error which I am getting. So like these are like how these is different kinds of error which we can observe. Then we can also see this. Uh, we just take an example of Taylor series. So Taylor series expansion of e power x. Let's say this is the Taylor series expansion of e power x, and we are using Taylor series to approximate the value of e power x. And I am taking 10 terms, and I also like I can also use the MATLAB function exp to get the exact value. So let's see at x is equals to 5 using the Taylor series expansion and also using the exact value of uh, e power x. How can we get uh, different like approximate and error values. So we know that how the Taylor series, like I'm just taking how many terms? 10 terms I'm taking. So I have to add 10 terms here, like f of 0 plus f of 0.5 plus like this. We have to go like till uh, f of 0 uh, dash plus x into x plus x square by 2 factorial. Like that, we have to go on doing this calculations. So this is how like we are doing it. Like we are writing this for loop to define the uh, uh, Taylor series of our thing. So and then we can all after doing the Taylor series, we can get the exact value and the approximate value, and we can compare how much error it is giving. So like can just take can just run this and just use CLC clear. Now I'll just run this as a section. So we are getting value of ex power p exp uh, which is how much 1.6487, and the exact value, this is the approximate value and this is the exact value, and there is like very much less error between the two. So then like if I let's say increase, or like then if I let's say decrease the number of terms, like if I take only two terms in the Taylor series, then if I just run this, now you can see there is an error, like error is increased. So the approximate value now we are getting is 1.625 and the exact value is 1.6487. There is some error. So as we increase the number of elements, the error should reduce. That's what uh, like because like we are truncating less values. If we are truncating more values, we'll get the more truncation error. So this is the truncation error which we are getting here. So this is the truncation error, and that's how it occurs in the Taylor series. So there is also like we can also see how much we can also see another thing, uh, how error will propagate when we have like lot of iterations. So let's say we are doing numerical differentiation. So numerical differentiation of sin x. I want to do the differentiation of sin x. Like I know the value of sin x, analytical value of derivative of sin x, which is cos x. But I want to do this numerical differentiation and compare it with the exact analytical derivative. So let's say uh, I want to get the differentiation at what is the value which I want to get. Like let's say pi by 4 I want to get. Uh, and then I can do forward difference like uh, forward. I can use the forward difference formula like that. Then I can take like how much uh, h values. Like I will take like different step sizes. Like I'll take from 10 to the power of minus 1 to 10 to the power of minus 6. So as I decrease the value of h, as we decrease the value of h, we will see how the error is varying. So obviously when you decrease the value of h, you expect the numerical differentiation to converge. Like, but it is not always the case. So we are doing the forward difference, we are using the forward difference and also the backward difference here. So we are also taking care of the errors, like we are also saving the errors which we are getting, like due to the central difference and the forward difference. And we will plot the plot and we'll see how the errors are propagating, like for different step sizes, like how error is occurring. Uh, let's run this. So, so you can see as step size step size decreases, you can see in the forward difference formula, uh, error is decreasing, decreasing, decreasing. But the error is like also comparatively more than central difference. Central difference uh, gives the like use less error because in central difference you use two terms of the Taylor series. In forward difference you use only one term in the Taylor series. Like if you know how you to get the formula for forward difference and central difference, you know it. So, and also order of error is h square. So that's why uh, as you uh, take reduce the value of step size, it also has, like you can see, slope of 2. This will have a slope of 1. So that's why it is very steep. The this line of central difference is steep. But you can see there is a peculiar phenomena which is occurring here. Like after this uh, 10 to the power of minus 5, like after this 10 to the power of minus 5, if you are reducing the step size further, you can see an increase in the error. This should not happen, right? Because we are further reducing the step size. But that is occurring because there is some numerical precision to MATLAB. Like it cannot go beyond a particular value in computation. Like it cannot go beyond 10 to the power of minus 16. If you are going beyond, like if you are like if you are getting some value below 10 to the power of minus 16, MATLAB will round it off and it will take only up to 10 to the power of minus 16. So that's why due to the truncation, due to the round of error which you are doing, so that will lead to this increase of error, like by when you further decrease the step size. So that's what, like we have to be very careful. Like we cannot infinitely, like we cannot take a very small value, step size value also while doing the numerical differentiations. There is a limit to it, like you cannot go beyond a certain value, like because it will obviously take, it can get some round of error and you might get like if you're taking 10 to the power of minus 7 on 10 to the power of minus 8, let's say I'll just plot up to 10 to the power of minus 8. That would give you a good idea. Like if you are plotting up to 10 to the power of minus 8, uh, you can see this, like you can see the error is like increasing. So like this should not be the case. Like this should go below it, but this line should go like this only. But this is happening because we are doing MATLAB. We are using MATLAB computations, and it have a inherent round of error which due to the machine precision, and that occurs. So we should be careful of taking the step sizes. So we cannot take like very very small values. Like we cannot go beyond particular value. So that's what like how uh, this we can see round of errors, and like how errors vary with step size that can be seen. And so it's like as you like uh, reduce the step size, like round of error will increase. So some kind of thing we have to maintain. Now let's also see a example of another example of e power x. Let's say this is our like I want to do the numerical differentiation of e power x, and I'm taking various step sizes. Like I'm using the central difference formula, and let's see how it will react, how we'll get the result. So it's taking a bit of time. Yeah, this you can see this error is like decreasing from 10 to the power of 0 to 10 to the power of minus 5, and after it it's like increasing like anything. So this should not happen. So round of errors are like very critical, and it should be taken care of well. We cannot go and decrease the step size as much as we want. Yeah. So that was about errors. Uh, so then we went and what did we go and learn? Uh, we went and did solve linear equations. So linear equations we saw, I think this was this was okay. Differentiations. And then we saw how we can solve linear equations. So there are like two methods of solving linear equations. First, first is the direct methods, like, and then we have also the iterative methods or indirect or iterative methods, whatever you can call. So we have the Gauss elimination method. We have the LU decomposition method. So depending upon the problem, and then in Gauss elimination also there is also partial pivoting. Like partial pivoting is like uh, we don't divide the first row by anything. Like uh, we just uh, we just extend the rows such that uh, pivot element should be the largest, and we do these kind of calculations, and we do it. So LU decomposition, Gauss elimination, and Gauss Seidel, and there is also Gauss Jordan method, which can also be used. So indirect solvers are there, like iterative solvers, Gauss Seidel and Gauss elimination. So and we have also seen today the tridiagonal matrix algorithm. So for solving instead of using Gauss elimination for banded matrices or huge tridiagonal uh, which are like sparse matrices, we can also use a tridiagonal matrix algorithm or the Thomas algorithm to solve to further increase the computational efficiency and also to save the memory. So this was this was the thing which we have done like in the week 4, which uh, occurred, and then we solved the numerical uh, the nonlinear equations. So in nonlinear equations, we saw Newton-Raphson bisection method, and this we have all like Newton-Raphson. We have solved the problem yesterday itself, like Newton-Raphson bisection method, fixed point iteration, and like we have solved a few examples. So that can be done. Like you can also use functions, like instead of like MATLAB inbuilt functions are also there. So so we have seen like how we can solve nonlinear equations. We can use the bisection method. Bisection method is like basically you take two initial values, assume, and then you calculate the then you see the uh, error and you go about it like um, till you go get some kind of convergence. You go on doing it. So and Newton-Raphson is like a different way, and yeah. So this was we were solving using our yeah, Newton-Raphson and these things. I think we can also use this function. What was that function? I forgot. Fsolve also we can use to solve the nonlinear equations, which is a inbuilt MATLAB function. So that is like a very simple thing. You can just remember the syntax and you can go about it. And then we went and we saw numerical integrations. So uh, numerical integration and numerical differentiation. So like we have these like lot of different methods. So numerical integration, we have a lot of different methods. We have the Simpson's rule, we have the trapezoidal rule. Uh, you can also use like trapezoidal rule for single steps, multi steps. So and like in Simpsons one third Simpsons there are like also like lot of different components of Simpsons like Simpsons rules. So that also we can use do the numerical integrations. So that's what we have learned in this module. Like this was the one example of it. And you can also like for numerical integration, there is also uh, one more method called Gauss quadrature method. And we have this Gauss quadrature also. Uh, uh, where is it? You can also use that function, inbuilt MATLAB function, to solve any problem. So this is numerical differentiation. Like we are like doing it regularly, like from past 4 5 weeks. Forward difference, central difference, backward difference, and all these things. Like yeah, we can also use Gauss quadrature formula. So where is it? Gauss quadrature. Just use help quad. So, so this is the syntax of it. Like you can use this to numerically evaluate any integrals using Gauss quadrature, like or adaptive Simpson quadrature. So like this is the syntax. You have to give the function, and a to a comma b are like up to from which point to which point you want to integrate, and this is the tolerance also which you can give. So, and there are like also this you can also use other uh, functions, inbuilt MATLAB functions like integral one. Integral is just like this is you doing analytical integration. Like this does for a single integration. If you are like having double integration, you do integral two. And there is also quad 2D which you can use like if you have to do integration in a two-dimensional domain. I think quad QK is what is this? Quad QK. So quad QK is Gauss Cronford quadrature. Okay. So this is also one kind of technique to do the numerical integration like trapezoidal rule or Simpson's rule. So this also has a MATLAB syntax which we can use to which we can call this function Gauss called 2k and use the syntax to numerically evaluate our integrals. So then we went up to the week 7. After doing this, then we saw solving our ordinary differential equations eigenvalue problems using various methods. Like we saw explicit method, implicit method. So explicit is like when you are taking the differentiation at the future point itself, and like uh, explicit is like when you are taking the differentiation at the present point itself, and implicitly is like when you take differentiation at the future point. So explicit method is stable. Explicit method is not stable. Like explicit methods, we know that explicit methods, like you, they are stable only for up to a particular value, or you can say they are conditionally stable. Implicit methods, whereas implicit methods are unconditionally stable. Like no matter how much ever you decrease the step size, implicit method will give you a result. Like it won't diverge and it won't give you errors like implicit algorithms does. So this is the implicit method algorithm which we are doing. Like we used, we can see this. We were solving using some. This was the function which we were using. We wanted to solve uh, dy by dx is equals to this something. So and yeah, so we can also calculate the errors and plot these things. So all these things. So this was the differential equation. Dy by dt is equals to minus 2ty. So and like this thing which we are getting after uh, we are solving the uh, nonlinear equation which we get. So after applying the Euler's implicit formula, you'll get a nonlinear equation and you have to solve it. Like we can use fsolve also you to solve the nonlinear equations, and we can get the. So there is also like Hume's method, which is also a kind of Euler's method only, and then we can also have the RK4 method. So this is a very most widely used method which we uh, can use to solve ordinary differential equation initial value problems. So RK4 is the most used method. Like you can use the OD45 algorithm, so which takes adaptive step sizes to for solve using RK4 method. So OD45 is a very good algorithm which we can use, but sometimes there are also a lot of problems. Like if your system is stiff, like let's say if your this uh, function on the right hand side minus 2ty is uh, like taking sudden jumps, like having like very sharp slopes, so rapidly changing or like whatever you can call, then this might not be very stable. You using our OD45 algorithm, then you can go for, then you have to go for implicit methods they like then you can use solvers like OD15s or OD23s, which are implicit solvers in MATLAB to solve our ordinary differential equations eigenvalue problems. So that's what we learned in the week 7, like different ways to solve OD 45 um, initial value problems for a single variable. And yeah,
Good evening, sir. Sir, can you just repeat the name again, sir? The implicit for implicit,
solvers.
yeah, solvers. Can you again
Im-
rename this, sir?
implicit solvers are these, right? OD15s, OD23s, OD15s, like help. OD15s. So, so this is our one function which we use solves stiff differential equations, and there is also OD23s. So you can see this is also OD23s is there. S
Sir,
is for stiff. Yeah.
and one more thing. Now,
Hmm.
if you go to some different means other software, whether
Hmm.
the name, whatever we have got here, remains the same there, or it will be defined some other way. We have to means there the
Okay. The
name will be
function
different, or yeah, that is the
function
inbuilt
names.
function. Yeah, inbuilt function. For
No, no,
example,
no.
OD45, some other name it will be or the same name.
Let's
Like
say
for
in
example,
Python. Yeah,
yeah.
yeah. No, no. There will be different names in Python. Like in Python, I think you can use alternative of alternative of OD45 in Python. Like integral something is there. So you can use, there is a library in Python called SciPy. So SciPy has uh, uh, this function called solve IVP. So you can use that.
Okay,
Uh,
sir. Thank you.
in that you can change methods also. Like you can use RK45, all these things, and there is also other OD solvers. But like if you want to use, you can like solve IVP. You can use. I think. Mm. For let's say if you want OD15s, then you can use a method called LSODA in Python. So first step problems you can use this, and yeah, like obviously the names changes. Like there, like these won't be same names. Like these are names in MATLAB.
Okay, sir.
Okay.
Thank you.
Uh, then can I just then we also learned about how to solve uh, OD ODs with multiple variables. So or ODs, ordinary differential equation with order 2 or order 3. So we can we can convert them into ODs again, like using the state space form that we saw in the week 9. I think, yeah, no, no, not in the week 9, in the week 8. So we saw this multivariable function. Like we can use this uh, mask pairing. Like example, you can see like we are converting a second order differential equation to two first order differential equations using the state space form. And then we can solve these first order differential equations using OD45, which is a algorithm to solve first order initial value problems. Or you can use RK4 or RK5. But if you like this, like if you want to use OD45 or RK4, you have to convert them into first order differential equations. So That's what we have to do. Like otherwise, if you want to solve it like a second order differential equation itself, you have to go like search for some methods. Like there are some methods like Newmark beta method, uh, and Wilson theta method, which we can use like to solve second order ordinary differential equations. But that will be also like not uh, very good compared to using OD45. So it's better to convert your second order differential equation into two first order equations and solve them. That will give maybe a much better result. So like that, we saw multiple like variables, like how can we solve OD initial value problems, and then we saw regression. So we saw how can we do regression. So regression is nothing but curve fitting. So you have uh, some, let's say, experimental data which you are getting, uh, like for some input, for you are getting some output, and you like you don't, obviously you won't have you won't have continuous data. You take experimental data at some steps sizes, at like at different points in time you can collect, and you want to fit a curve which best passes through that, through those points, and then like you can use regression. So linear regression is like basically we are doing uh, sum of squared of errors, and we are trying to minimize the squared error. That way we can get some value for the coefficients of the polynomial which we are trying to fit, and those coefficients are uh, are calculated by this linear regression calculations, and you can fit any curve like whatever you want, which passes through this. So that is linear regression. Like we can use, like we can do this linear regression. We can do this thing, or we can also use this function which is inbuilt MATLAB function, which is LSQ curve fit, uh, to do the curve fitting. So that is also one way of doing it, and they like we can also uh, then we have seen, I think we have also seen interpolation. So interpolation is a different thing. Like interpolation is something uh, like this is, I think, yeah. We can also do nonlinear regression. So we can use LSQ nonlinear, like this function, and we can do the nonlinear regression directly. So, and we have also seen temperature of yeah, yeah. This is an example like which in which like there are different temperatures given for a day, and we want to calculate a temperature at some different points of time in the day. Like we want to get uh, uh, interpolation. Like interpolation is nothing but like you don't know some value, like you have a lot of values like 0 to uh, let's say uh, 1 o'clock, 2 o'clock, 3 o'clock. But if you want to, let's say, calculate like you want to know what will be the temperature of uh, place at like 2:30 in the night. So obviously, if you have all this data, like this is already like this is obviously like following a certain pattern. Like you cannot just have a random value of temperature. Like between 2 to 3 hours, there will be a change. Like there will be a change. Like it can go from 25 to 26 or 25 to 27, like that. Like there will be a pattern. So that we can do by using this spline interpolation. You can also like this is one way of doing it. Like we can use the spline interpolation. Like and we also have this, I think, P-chip interpolation. So where is it? Inter temperature. Yeah, yeah. This is also, yeah, P-chip interpolation is also there. So there is some. Uh, this frequency, like if you use the T-chip and spline, like uh, let's run this and see how it's happening. Like you can see, this is the spline interpolation, which is spline interpolation is giving this kind of curve, but like this should not happen because speed, like you cannot uh, like speed is decreasing like from 0 to, like this is this decelerating. This should follow this path, like it should not like uh, increase like this. So instead of using, in these cases, instead of using the spline, we have to use the p-chip interpolation. So that's uh, way more accurate. Like, and also you can see that this is going below 0. Like speed cannot go below 0. That's not possible. So that is one thing. Like here, just like in between 2 points, you are just trying to fit a like uh, line here like that. So p-chip interpolation takes care of these things, and then in the week 10, we learned about finite difference, like uh, finite difference for solving differential equations, like boundary value problems. So we saw shooting method also, and rod conduction problem, like two different problems we saw. So like how can we solve boundary value problems, like using the ghost point approach, or also the shooting method that we have seen, like, and also uh, we have seen this differential algebraic equations, like we have not discussed it, like we won't discuss it, like this is uh, just an extension, extension, like you can see the video and learn. Like, and also I don't think they are going to ask this exam. I think that was a bonus like there. And then after that, we saw in week 11, last week, we saw how can we solve partial differential equations. We used method of lines, like for parabolic and hyperbolic. And there are also like for elliptical equations, also some bonus lecture how to solve them. So, and in the last week, we have like last yesterday we saw like how can we solve ODs, partial differentiation in multiple variables. So like this was like a very comprehensive course, and we learned a lot of things from starting to use how to how to write code in MATLAB to how to implement like various multiple numerical methods, ranging from numerical differentiation, integration, regression, solving ordinary differential equations, partial differential equations. So we have come a long way. Like we have come, like we have learned a lot of things. Uh, that's what this course was all about. Different uh, things which we have learned, like uh, this can also this is not just a programming course, but also a course for learning numerical techniques also. So I hope this course has helped you all to learn a lot of things, and hopefully the sessions which we had, these extra sessions, also have contributed in some way or the other, like maybe not as good as the lectures of professor, but it might have helped you to solve some doubts, or some kind of explanations which you might have missed in the course videos, like I try to incorporate here and there. So I hope it might have helped you. So, and to like with this we will end it. Like this was our last session, extra session, and like from here uh, you can just prepare for your exam, and hopefully you uh, 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 give the exam properly, and like get some good learning from the course and use it in your future for research or other purposes. Like maybe you are doing some course in your college and you want to solve some problem, like then you can use MATLAB or some other programming language and do it in a very smart way instead of using uh, hand calculations. So that's what we could do today, and hopefully, I think I have summarized everything. Like time was less, so whatever I could summarize, and hopefully you go and revise again, and you'll get a good idea of everything. Do you have any doubts? Any other doubts or clarifications if you want from me?
Sir,
Yeah, no,
yes, sir. So first of all, thank you very much, sir, for all your
yeah,
inputs and knowledge
yeah,
sharing. From my end, there is no doubt, sir. So for the last time, can you just again share your email ID, sir?
yeah. Uh, just here in the chat box.
Yes, sir.
You can mail it. You can mail me.
Uh, Fine. Thank you, sir. Thank you very much again.
Also, thank you for joining. Like otherwise, like one or two people were joining, like three people were joining, and you were also like very regular. So that made the class more interactive. Otherwise, I could be just speaking to the computer. So thank you also for joining and patiently, like whatever I was